After seeing first order linear differential equations, next let us start chapter 4, which is about higher order linear ODEs. Let's start by recalling the definition of a linear ODE. A linear ODE of course means ordinary differential equation. In the dependent variable y and independent variable x is an equation which either is already in or can be expressed in the following form. A0 of x, so this is a function of x only, times the nth derivative of y with respect to x plus a1 of x times the n minus 1th derivative plus and so on. In that pattern it goes, and eventually we reach an minus 1 of x times dy dx plus an of x times y equals capital F of x. So these are functions of x only, the right hand side also. And then there are some other things also which I will write now, where the function a0 of x is not identically 0. This means that it's not the constant function 0. It is non-zero somewhere. For some values of x, a0 of x is a non-zero real number. And additionally, we are going to assume some things. We assume that all these functions, all these ai's and f also, the right hand side, these are continuous in some interval of real numbers. And additionally, see, the condition that we stated here, that a0 of x is not identically 0, actually the author makes it even stronger than that. Additionally, the assumption is that a0 of x never becomes 0 inside that interval. For any x coming from this interval, a0 of x is non-zero. As an example, we can consider this second order linear ODE. D squared by dx squared plus 3x dy dx plus x cubed y equals e to the power x. So this satisfies all those conditions. First of all, this is linear, and the second thing is that you look at the coefficient functions. A0 of x in this case is the constant function 1, that is continuous throughout the real line. Also, it never becomes 0. So that means inside any such closed interval also it's continuous and it's never 0. A1 of x here is 3x, that is continuous. So we only need continuity for the other ai's. X cube is also continuous, it's a polynomial function, and the exponential function is also continuous. So it's the type of equation that we have here. And here is another example. This one is of order 3. Third derivative plus x times second derivative plus 3x squared times first derivative minus 5y equals sin x. Here also the first coefficient is the constant function 1, just like this one. Then the second and third one are polynomials, so they are continuous. The first one is also continuous. This one is constantly minus 5, so again continuous, and sin x of course is also continuous, and these are continuous throughout the real line. So in particular they are also continuous inside any closed interval, so it's also that type of equation. And now we come to the main part, where we have a theorem. This theorem is going to tell us something about existence of solutions of such equations. So let's see how the theorem starts. So again we have considered an nth order linear ODE, which is just that one that you saw just now, where again we have those conditions. So there is no need for me to again repeat these things. These are continuous, and that a0 is never 0 inside this closed interval. Okay, so then what does the theorem say? Then for any real number x0 in this interval and real numbers c0, c1 and so on up to cn minus 1, there exists a unique function f defined on that interval and real valued of course, that is a solution of this differential equation, and that also satisfies these extra conditions, that its value at that x0 is that c0, the value of the first derivative of the function at x0 is c1, and like that it goes. The value of the n minus 1th derivative at x0 is cn minus 1. This is an existence theorem. It tells you that if you have a differential equation of this type and you also have these other things, then there exists a unique solution of the equation which also satisfies these things. Existence and uniqueness theorem, of course, you can say. However, the theorem does not tell you how to find this f if you have such a concrete equation. We will come to those things later. Right now we have this existence theorem with us. And let us again go back to those examples and see what this theorem can tell us about them. Instead of just considering a differential equation, we consider an initial value problem. Here the differential equation is just that equation that you saw in example 1. And along with that we have these initial conditions. Y of 1 should be 2 and the first derivative of y at 1 should be equal to minus 5. So we note that those conditions are true in this case. That means the coefficient functions 1, 3x, x cube and that right hand side e to the power x, these are all continuous throughout the real line. So in particular they are also continuous in any interval of this type which contains this 1. And because of that, by that theorem, this IVP has a unique solution defined on that interval. Note that in this case, 1 is your x0, c0 is 2 and c1 is minus 5 and c1 is cn minus 1 because n in this case is 2. In this next example, the differential equation is this third order differential equation. 2 times the third derivative plus x times the second derivative plus 3x squared times the first derivative minus 5y equals sin x. So you can see that those conditions are true here. All these coefficient functions are being polynomial continuous throughout the real line, and sin x of course is also continuous at every real number. In particular, they are also continuous inside any interval that contains this x0. x0 in this case is 4. And that is why by the above theorem, this IVP also has a unique solution inside any interval that contains this 4. In this case, x0 is 4, c0 is 3, c1 is 5 and c2 is minus 7 divided by 2. We have only this because the equation is of order 3. Now that theorem has a useful corollary also. Let's see what it is. This time we start with a function f defined on some closed interval a comma b, real valued function of course, which is given to be a solution of the following homogeneous linear equation. That means again our linear equation of order n. But homogeneous means that the right hand side function is 0. That right hand side function capital F is usually called the non-homogeneous term. When that is identically 0, then we say that the equation is homogeneous. In that sense, it's homogeneous. And of course, the other conditions are also there. These AIs are all continuous inside this closed interval, and A0 never vanishes inside the interval. Alright, so then what is the conclusion? This is the conclusion. If you find a real number x0 in this interval at which the function value is 0, first derivative value is 0, second derivative value is 0, like that all the way up to the n minus 1th derivative value, that is also 0, all these values are 0, then that solution f must itself be 0 throughout this interval. That means it's identically 0. So at least in this case, you know what the solution is. It's the constant function 0 in that interval. In general, you don't know, you just know that there is a unique solution, but in this case, you know what the solution is. And because of this corollary, the following IVP has the 0 solution. What is the IVP? It consists of this third order differential equation, linear, the third derivative plus 2 times the second derivative plus 4x times the first derivative plus x squared y equal to 0. So you see that the right hand side is 0. Also, the coefficient functions, all being polynomial functions, are continuous throughout the real line. And these are the initial conditions. At the input 2, all the values should be 0. So everything matches with what we have in the corollary. So that is why the unique solution of this IVP in any interval which contains that 2 is the constant function 0 on that interval. And let me end the video here itself. In the next video on differential equations, we are going to focus on homogeneous equations, that is those equations whose right hand sides are 0. And there we are going to see a theory of solutions of such equations, where say 2 or 3 solutions are already given. How can you use them to generate more solutions? And here you will see ideas from linear algebra, linearly independent solutions, solution spaces. So we will discuss those things.